time we talked about really sort of the atom. We talked about some experiments, for example, that led to sort of the understanding of the structure of the atom. Remember that the atom basically in the center has a positively charged core, which is known as the nucleus. That is where we find protons, which are positively charged. We also find neutrons in the nucleus, which basically have no charge. And pretty much as we kind of talked about with Rutherford's experiment, pretty much most of the atom is empty space. And it's really within that empty space where we have our electrons, which are negatively charged particles flying around. As we talked about, basically the electrons fly around in a fairly random sort of pattern. They do not fly around in pretty circles like in orbits or anything like that. They do travel pretty randomly about the nucleus. There is obviously an attraction between the nucleus and those electrons, as the electrons are negatively charged. The nucleus is positively charged, so there definitely is some attraction between them. The most of the mass of the atom, as we talked about, is made up of the nucleus, and that really does make sense because both a proton by itself and a neutron by itself, they're both, again, about 1,800 or so times heavier than any electron that's flying around. So because the protons and the neutrons are pretty much in the nucleus, and they're pretty much way heavier than any electron, it does make sense that most of the mass of the atom is made up of that nucleus where we have those two things. Now, we also sort of talked about the idea that everybody does have protons, electrons, and neutrons. The one exception to that is hydrogen. Hydrogen only has a proton and an electron. It does not have a neutron. But pretty much every other element will have both, or all three, I guess, protons, electrons, and neutrons. We also started talking about sort of the idea of isotopes. Isotopes are really the same element, but they have different masses. And what makes them really have different masses are the number of neutrons. So they will have different numbers of neutrons. And as we talked about last time, it is really the number of protons which determine what element you're talking about. If you change the number of protons, then you actually change what element you're talking about. The number of protons in an atom is a special sort of name, and that's what's referred to as the atomic number. The atomic number is the number of protons that we find in an atom of in an actual atom of the nucleus, I guess, the nucleus of an atom. We also talked about the mass number. The mass number is the number of protons, electrons. I'm going to say that right. I'm sorry. The mass number is the number of protons and neutrons. So mass number, protons, and neutrons that we find in an atom. When you are asked to calculate, as we talked about last time, atomic number, mass number, protons, electrons, neutrons, they all should be positive whole numbers. And that brought us to a conversation about the periodic table. Remember that only the atomic number can be found on the periodic table, and that is the number that's above the symbol. So the number above the symbol is the atomic number, which is the number of protons. Remember that sort of second to that, that if it is a neutral atom, the number of protons will equal the number of electrons. But again, if you're sort of, as we talked about last time, if you're asked a direct question like what is the actual definition of atomic number, the definition of atomic number is just the protons. But second to the definition, if it is neutral, it will also tell you the number of electrons. So sometimes people mistakenly think that the atomic number is both protons and electrons. And that's really not the case, as I think we did a couple examples towards the end there, where we did have something that had a charge. And when something does gain a charge, because the protons cannot change, otherwise we change the element, it is actually the number of electrons that do change. So atomic number solely, the number of protons is really the definition of it. You can find it on the periodic table. The mass number, on the other hand, like we talked about, will not be found on the periodic table. So remember that the number below the symbol on the periodic table is not the mass number, but again, it sometimes confuses people because it is a number that is very similar sometimes to the mass number. That is actually the atomic mass, which is, I think, what we talked about at the very end last time. The atomic mass is basically the mass of all the protons, electrons, neutrons that you have in a particular atom. Remember that the way we sort of find the atomic mass and really what we see on the periodic table is the average atomic mass of all the naturally occurring isotopes. So those were the calculations where we took like the percent abundance times the atomic mass of the first isotope plus the percent abundance times the atomic mass of the second isotope, and continued on sort of in that pattern. So again, the atomic mass that we see on the periodic table underneath the symbol, not the mass number. The very sort of simple way to remember that is that basic thing that I said earlier, that the mass number, atomic number, protons, electrons, and neutrons, they all has to be whole numbers. So if you look at a periodic table and you look at all the numbers, as we talked about last time, underneath the symbols, pretty much none of them are whole numbers. They're all like decimal numbers and stuff like that. So that's a good way to remember not to use that atomic mass as your mass number. Any questions on any of that stuff we talked about last time? Okay, let's see here. What did I just do there? Get that out of my way. Try that. There you go. All right, so I think this is about where we left off. So now we're going to kind of officially sort of talk about the periodic table. We're going to talk about, the different parts of the periodic table, and obviously things that you should know from the periodic table. So let's take a look at it. That obviously is a periodic table. It is an arrangement of all the elements. And actually, when they were putting it together, they did a fairly good job. They kind of left some spaces near different elements, and that allowed them to, kind of fill it in as they continue to discover sort of elements and stuff like that. This is the classic sort of shape of the periodic table. I will say that depending on sort of when your periodic table, sorry, come back, maybe keep going forward, go that way. There we go. Try that again. Maybe I'll do it. Let me see. Maybe I won't do it. There we go. Get something to write with here. There you go. So depending on when your periodic table was made, you'll see some variations a lot of times in this sort of region of it over here. And that's a lot of times on periodic tables, where they'll put sort of elements that they haven't maybe officially made elements, deciding whether they should be elements or not. So you'll sometimes see a lot of variation, more sort of towards the bottom, in this sort of range here. And in terms of, symbols and stuff like that, sometimes you'll see some weird symbols in that range. And sometimes you may even not see anything sort of in that range. And again, sort of depends on when your periodic table was made. But that's usually where they kind of stick elements of, like, we're not really sure yet if it is going to be an element and that type of stuff. So let's talk about the different parts of a periodic table. First off, when we go up and down on a periodic table, that is what is referred to as a group. And you'll see a lot of different numberings. For example, this particular periodic table here has like A numbering. You also see some B numbering, and you'll see just some straightforward 1 through 18 numbering. And again, depending on your periodic table, you may see these different types of numbering. You may not see the numbering. You may just see one sort of type. For this chemistry class, and probably any chemistry class that you take, we always use the representative numbering, which is essentially the A numbering. So we use the A numbering, and that means over here, lithium, and we'll talk why lithium here and not hydrogen, but lithium going down is group 1, beryllium is group 2. We actually skip the middle part here, and we come over here to where boron is. That is group 3, group 4, group 5, group 6, group 7, and group 8 there. So we always use that representative numbering here are the A numbering. Very rarely in a chemistry class does anybody kind of use that the B numbering or the other numbering. We typically do use that A numbering. In addition, most of the time, people don't really go 1A, 2A, 3A. They just basically say group 1, group 2, group 3, group 4, and so forth. So you absolutely put the A in there, leave the A is perfectly fine. But a lot of times people will sort of leave the A off, if you will. If you're old like me, not too many people call them families anymore. Most people call them groups. And again, so groups going up and down on the periodic table. Periods, on the other hand, go left to right, and there's 7 periods. So going that away is period 1, going that away all the way across period 2, period 3, period 4, period 5, period 6, and period 7. So going all the way across are our periods on the periodic table. Up and down our groups. We already talked about the last thing here, which is the number above the symbol is the atomic number. So as we talked about earlier, that obviously is the number of protons that we have. So remember that every single element has its own atomic number. It never repeats. And that's why earlier when we were talking about if you know the number of protons, or the atomic number, which is essentially the same thing, you should know exactly what element you're talking about. Now, when we look at a periodic table, it is really broken up into sort of 3 categories. There are metals, nonmetals, and metalloids, which are sometimes called semimetals. And on most periodic tables, you typically will be able to see what is oftentimes referred to as like a staircase. So like this right here, kind of the staircase coming down, coming down. And pretty much to the left of the staircase, these are metals. And also there was those 2 rows at the very bottom. Those guys are also metals. And metals are good conductors of heat and electricity. They can be hammered into thin sheets. They can be pulled into wires. Typically speaking, metals have a shiny appearance. Most metals are solids at room temperature. The one exception is mercury. Mercury is actually a liquid. And a lot of times on a lot of periodic tables, you'll actually see mercury sort of a different color than the others. So you'll sometimes see that as well. Now, up to the right here, above the staircase, that is where we have nonmetals. And as we'll talk about, pretty much nonmetals have the opposite sort of characteristics. They're kind of dull and shiny and so forth. But this brings us to sort of the point I was making before. If you remember, this is lithium over here. That is hydrogen. And group 1 actually starts with lithium and not hydrogen, because hydrogen is a nonmetal. And everybody else here in group 1 are metals. So although hydrogen is hanging out over here pretty much on every periodic table you see, it is not part of group 1 because it's really not a metal, it's a nonmetal. Years ago, on older periodic tables, you may even see hydrogen laid up over here as well on both sides, and then helium is here. So years ago, they a lot of times would put hydrogen on both sides. And as we go through different chapters throughout the semester here, we will see sort of some different properties associated with hydrogen, and it has some unique sort of characteristics. So sometimes, years ago, they actually used to put it kind of on both sides of the periodic table. Now, as I mentioned earlier there a second ago, nonmetals are really sort of the opposite in sort of characteristics. They are poor conductors of heat and electricity. They have a much more varied physical sort of state. Some nonmetals are gases. So a lot of those elements that we talked about, which are diatomic molecules like hydrogen, oxygen, nitrogen, fluorine, chlorine, and so forth. A lot of those guys come as 2, and they're gases. Bromine, which also comes really as a 2, is a liquid, and there's some that are solids like carbon and sulfur. So unlike sort of metals, we do see a much more varied sort of states than we do in the metal state. Lastly, here are metalloids, which again are also sometimes referred to as semi-metals. And just to sort of cross-lay it here, some books, and I really don't recall off the top of my head, some books will include boron as sort of a metalloid or semi-metal. But, you know, the staircase sort of starts in that region and then kind of comes down as two. So as you can see here, basically these guys here. And these guys, in terms of metalloids or semi-metals, in terms of characteristics, you could have the same element pretty much have characteristics that are very similar to metals. And then you also could have the same element, which will have very similar characteristics to non-metals. And it does sort of make sense if you think about sort of its location. The metalloids are kind of going from metals to non-metals. So these metalloids really do fall sort of on both sides of themselves in terms of characteristics. They have basically some characteristics that would definitely be classified as metal characteristics. And again, the same element would have some characteristics that are classified as non-metals. So a lot of semiconductors, for example, sort of in that range as well. Now, when we look at the periodic table, there are certain groups that actually have special names, and you do need to obviously know the special names here. So starting again here at group 1, which starts with lithium, I guess the circle. That is what is referred to as the alkali metals. So the alkali metals are lithium, sodium, potassium, rubidium. Right next door, where beryllium is, are what are referred to as the alkaline earth metals. Those are group number 2 on the periodic table. Group 1 and group 2 on the periodic table is where we find a lot of bases kind of come from. And that's really what alkaline means. Alkaline means basic. So we get a lot of our sort of strong bases, as we'll talk about maybe in the acid base chapter, actually come from guys in group 1 and group 2, like sodium hydroxide, potassium hydroxide, calcium hydroxide, strontium hydroxide. So a lot of these guys in group 1 or group 2 that kind of hook up with hydroxide really are sort of the basis of where a lot of strong bases come from. Going down there to group 7, where we have a lot of our diatomic guys, our fluorine, chlorine, bromine, and iodine. Those are what are referred to as the halogens. And the halogens, they're all non-metals over there. And again, the vast majority of all of them do come as diatomic molecules. And what we see here, and what we'll see on the next slide, right next door, in group number 8, we do have what are referred to as the noble gases. The noble gases are also sometimes referred to, again, if you're a little bit older like me, and again, people don't really call them rare gases all that much anymore, but noble gases. What noble gases, which is group 8, basically means is they're sometimes referred to as being chemically inert. And chemically inert basically means that they are unreactive. So they're kind of chemically inert. They're unreactive. They really don't react with anything. They'll react with themselves, but they're really not looking to react with anybody else. They're really important, especially in the next chapter that we'll talk about, because the basis pretty much of all bonding, as we'll talk about a number of times, is basically everybody wants to end up like the noble gases in terms of their electron configuration, because they're very, very stable. So group 8 or noble gases, kind of the goal of everybody, and especially when we talk about bonding, is sort of the goal of why things bond and how things come together when we do bonding. The two rows kind of set there on the bottom is really because, you know, your periodic table would be ginormous. If you sort of follow the numbering here, atomic number, this guy right here is 57. And then we jump to 72. And really, this row right here has 58 and so forth. Technically speaking, actually goes right about there. And same thing if we go right below it, this is 89. Then we jump to 104. And here's number 90. And this row right here, which again are also metals, technically goes right about there as well. I've only ever seen one periodic table actually built with that in the right locations, and it took up an entire wall because they had to move everybody way to the right to fit those guys in there. So that's why they're typically put on the bottom. But technically speaking, if you follow the atomic number, those two rows should go there. They're called the lanthanides and actinides because those are technically the two elements they should follow. So that's where those sort of names come from. That also leaves us one last sort of section on the periodic table, which is really important, and that is the transition metal region. So between group number 2 and group number 3, we have our transition metals. So again, all these guys in here, basically, I over swipe there, come back, try that again, there you go. So basically, let's try that again, there you go. Kind of everybody, you know, in this region here, those guys are the transition metals, as we'll talk about when we talk about naming. They also do have some interesting sort of properties, one of which is they do, when they make charges, can make a variety of different charges. So for example, iron, which is Fe, in certain cases can make a +2 charge, in other cases can make a +3 charge. So, you know, they have some unique properties in terms of what's going on. These two rows on the bottom that we just talked about here, because they technically go into here, these two rows are sometimes referred to as the inner transition metals because they technically go right there with the transition metals. The good news, I guess, for us is we really don't deal too much with those guys on the bottom. I might have mentioned it earlier, but we really don't deal too much with those two rows on the bottom. Probably the only element we'll probably see pop up, I would think, would probably be uranium. Again, that could pop up. But other than that, we don't see too much. For the most part, most of those guys on the bottom two rows are also radioactive type elements. And a lot of them are, for example, sort of man-made ones, things like californium, einsteinium, nobelium, you know, those kind of guys. That's kind of where those radioactive type guys end up. Now, in terms of the periodic table, you need to know pretty much what we just talked about. You need to know groups, which way they go. You need to know, obviously, the numbering of the groups, which again is group 1, group 2, skip the middle, group 3, where boron is, all the way to 8. You obviously need to know which way periods go. You need to know on the periodic table what guys are metals, which ones are non-metals, and which ones are metalloids. And you do need to know, obviously, the special names of those groups, where the alkali metals are, the alkaline earth metals, halogens and noble gases, and obviously where the transition metals are. Any questions on the periodic table there?
Professor Efron,
Yes,
if for any reason we were to be asked what element does the alkaline column start with, if we put hydrogen, would that be correct, or we have to go with lithium?
Yeah, so if you're asking here in group 1 for the alkaline metals, it would actually be incorrect to say hydrogen because, again, hydrogen is actually a non-metal.
Yes.
And everybody else here, hence the name alkaline metals, they're all metals. So lithium absolutely is the first one that is part of group 1, even though on every periodic table you ever look at, hydrogen's hanging out over there. And just like this periodic table, they put the one above hydrogen. It's actually technically not part of the alkali metal or alkali metals.
All right, thank you.
You're welcome. Other questions?
I have a question. So would hydrogen be part of group 7A?
I'm sorry, say it again.
Would it
Hydrogen.
be part of group 7A?
No, hydrogen is really not part of a group. It's just kind of by itself, if you will. And again, because it really does have a lot of special sort of properties, even though sometimes you'll see hydrogen over here on some periodic tables, most of the time we really don't associate any sort of group with hydrogen as being part of any special group, because it's definitely not part of group 7, which are the halogens. So hydrogen is definitely not a halogen, so it wouldn't be considered group 7. Other questions? Okay. So now that we sort of talked about the periodic table, we talked about the atom earlier, we're now going to kind of focus in on kind of electrons and electron configuration and sort of how electrons are distributed within the atom. And first off, you know, a lot of times when we talk about electrons, and there's certain things that do happen with electrons, and that is when we have electrons, they are on different energy levels. So for example, n equals 1, n is sort of like the energy level. And maybe there's like an n equals 2, which is a higher energy level, n equals 3, which is a higher energy level. And as electrons get excited, for example, and they get excited in many different ways. So for example, like fireworks, right? When you launch some fireworks at a professional show, I guess, right? You know, they basically, you know, explode, right? And there's some, you know, sort of explosion, which provides a lot of energy. And what happens when that occurs is all the electrons and the elements in those fireworks, they get excited and they end up going to like a much higher energy level. And a very common thing in sort of chemistry is this: things in high energy level are fairly unstable. Things don't really want to be in high energy levels. Things really want to be in sort of lower energy levels. So these electrons that get sort of excited upwards will eventually kind of work their way back down to a lower state of energy. But in order to do that, they have to give off the energy. And they give off the energy in the form of a photon of light or that has a specific wavelength. Now, if that photon of light has a specific wavelength that, for example, falls in the visible part of the spectrum, then we see the pretty colors of the fireworks. If you've ever done like a flame test, take a sample of something and put it into a flame. You maybe have done a flame test without realizing it. If you've ever boiled water, for example, on your stove, and if you've ever had that water sort of overboil, very common when you make pasta, right? All of a sudden the water goes over, and some of the water actually hits the flame. If you have a sort of a gas and flame under there heating it, you might notice that the flame actually changes color as the water hits it. And a lot of times that's a result of the sodium from the salt in the water, basically the electrons and sodium being excited, and you see maybe like a yellowish type flame that kind of occurs as it sort of overboils. Now, not all the time when electrons get excited and stuff that we see colors. And there's different parts of what's referred to sort of as the electromagnetic spectrum, which is what we're looking at. But there's a very important sort of relationship between wavelength of a wave. And by the way, when we talk about a wave, it's really just movement of energy through space in the form of a very badly drawn wave there. And the wavelength, which is sometimes abbreviated as lambda, is basically the distance between two peaks in a wave. And this is moving with a certain amount of energy. And basically, if we have a longer wavelength, it basically also will have a lower, what is referred to as frequency. Frequency is basically, you know, how many times a wave passes a point in a given second. And it will have a lower energy associated with that. As opposed to if you had a wave that had a much shorter wavelength, sort of badly drawn again, but we'll go with it. Here is the wavelength for this one. This is a much shorter wavelength. It corresponds to a much higher frequency as it keeps occurring obviously much more often kind of occurring. And it also carries a much higher energy. So the relationship between wavelength and sort of energy is longer wavelength, lower energy, shorter wavelength, higher energy. And there's very common things that we see. For example, if we look at the wavelength here, that's like 10 to the 5th, which is a much larger number than if we go all the way over here to the right. And I'm too old to read that, but I think that says 10 to the minus 11. That's a much smaller number. And that means that on this side of the electromagnetic spectrum, we have much longer wavelengths and much lower energy, as opposed to as we rotate down the other way, we have a much smaller wavelength, as you can kind of see here with the wave, and a much higher energy. So for example, in the kind of longer wavelength, we got things like radio waves, television. This is why, it's not too bad to listen to the radio as we're driving around in the car. Not a lot of energy associated with that. As we kind of continue down the spectrum, we get to like microwaves, obviously cell phones as well, but microwaves past that. Microwaves have really enough energy to kind of spin water molecules really fast, and your pizza is cooked in a few minutes. Continuing down next is infrared. Infrared is typically where we feel heat. Again, we really won't see much color or anything like that, but it's kind of where we feel heat. Again, more energy associated with that. Then we get to this part of the spectrum, which is the visible part of the spectrum. And that's really where we see color. So like the fireworks example, like the water over boiling example, that's where we see our, Roy G. Biv, right? Red, orange, yellow, green, blue, indigo, violet. And that's where we see different colors in the visible part of the spectrum. And even within the visible part of the spectrum and colors, there's a difference in terms of energy of those colors. We see red over here at 700 nanometers, which is a much larger wavelength than what we see over here where violet is at like 400. This is much shorter. That is much longer in terms of the wavelength. So in terms of energy, red is actually lower in energy color than violet is. So even within the colors, there's a difference in terms of the wavelength and also in terms of the energy that's associated with it. So this is typically where we see color. So if those electrons are transitioning from different energy levels and they give off a wave that the wavelength corresponds to somewhere in that particular spectrum, we then will see that color. Continuing past that, we get into ultraviolet. That is UV. That is also a little bit higher in energy. That is why we put sunblock on, right, when we go outside, so we don't get crispy and burnt and all that good stuff. Next to it is X-rays, which is much higher in energy as well. That is why typically when you take an X-ray, they throw on perhaps a lead vest on you, and the person taking the X-ray steps out of the room so they don't get exposed to it. And then we have at the very end of the spectrum here, really high in energy, very short wavelength. That is gamma rays, and gamma rays are really just kind of pure energy. They're radioactive sort of rays, and they're really very, very high in energy. As you can tell with X-rays, they do all that precaution. Gamma rays, you sometimes do a lot more precautions, lead barriers and stuff between people as you're working with something that gives off gamma rays and stuff like that. They can penetrate very, very far, for example, in the body and in tissue. So this is electromagnetic spectrum. I'm going to say what you need to know on this is just the order, if you will. Like radio waves are, again, on this side, which is our longer wavelength, lower energy. And on this side, we have our shorter wavelength and our higher energy. So you just need to kind of know the order at which they go. Like if you're asked to put them in order based on energy, you'll be able to kind of put these guys, again, this is the visible part of the spectrum, in order based on something like energy or wavelength. You don't need to know exactly where any of the numbers sort of break off. Any questions on that there? Okay. basically the same picture. All right, so identify the form of electromagnetic radiation in each pair that has the greater energy. So again, somewhat questions like this. These are our differences between color. And again, what we would want to look at, for example, we could look here, yellow, which is like in this area between 5 and 6. And it was blue, I believe, right? Which is kind of over in this area. So we see that the shorter wavelength is with the blue light, which would mean it has higher energy. Again, looking at ultraviolet versus infrared, again, we see infrared is over here to the left, which is where our longer wavelength was. And we're comparing that to ultraviolet, which is over here. Again, why we put sunblock on there. So we would expect the UV there to have a much higher energy. X-rays versus microwaves. Well, we don't usually put lead vest on and leave the room with microwaves. So I would assume that X-rays there would be the one that has the higher or greater energy. Any questions on that? Okay. So when we heat an element and we sort of pass the light through what is referred to as a prism, the prism is something that will sort of separate out the light into its component wavelengths. We get what is sometimes referred to as an atomic spectrum. And more specifically, elements give what are referred to as line spectrums. And line spectrums are different than what are referred to as continuous spectrums. And that is because something like the sun gives off a continuous spectrum. What is the difference? As we will see, kind of the difference between like a continuous spectrum, which is kind of like what the sun gives off, and like line spectrums, which is what elements give off. And by the way, this is why they're called line spectrums, because you get these distinct lines that occur at specific wavelengths that correspond to specific colors. The difference is really, the best way to sort of think about it is elements and their electrons, as they move from one energy level to the next, they're what are referred to as having quantized energy. And that's really a fancy word for saying when an electron goes from one energy level to the next, it will either gain enough energy to completely go from here all the way up to the next energy level, or if it's going in the opposite direction, it will lose enough energy to completely go up down to the next energy level. You'll never find like an electron going, well, I don't really have enough energy to get to this energy level, and I don't really have enough energy to get down to the other energy level. I'm just going to hang out in the middle between the two. So you'll never sort of find that. The kind of logical explanation of it is, or you can sort of think about it like stairs, for example. When you are walking stairs, for example, it's a lovely drawing of stairs. Most people have enough energy to go to this step and then maybe go to this step. Most people, when they're walking stairs, don't stop halfway through the step and go, I'm kind of tired, or I don't really have enough energy, because frankly, you'll fall, right? And that's not what typically happens. So quantized energy, and as these electrons transition from one energy level to the next, you could think of it that way. We will know that the electron will either be on this energy level, it'll be on this energy level, it'll be on this energy level, but it will never find itself sort of in between. And that's what happens with elements. And that's what we actually see with these lines. This particular kind of purple or bluish line represents a particular electron that has transitioned fully down from one energy level to the next, while this red one or orangey type one over there represents an electron that has transitioned also down from another one. The difference is one of these transitions may be a lot more energy, which we would expect this guy to be based on our conversation there about colors. This one, a much smaller difference in energy, would be more of the reddish type color that we actually see over there. What is the difference between that and a continuous spectrum? I kind of liken a continuous spectrum to, instead of you're walking stairs, for example, you're walking like a ramp, right? So let me draw a really bad ramp here. So this is like a ramp. And basically on a ramp, you can decide anywhere along the way to stop, right? It's possible. You're not going to fall. You could walk up a ramp or something like that and lay it up anywhere you want. When you're walking stairs, you really do have to get yourself from every step. Otherwise, you're going to fall. So this would be more of a continuous spectrum. This is more of a line spectrum. And this is more quantized energy, which is basically what elements do. Any questions on that?
Professor, a quick
Yes, sir.
question on the line spectrum
Yeah.
or either of them. How would you know if the energy, if the element's going on an upper or lower in energy?
Are you asking, how do you know if the electron is going down in energy or up in energy?
Yeah, yes, based
Yeah,
on just the
yeah.
on just the image.
So that's a good question. There's actually two types of sort of spectrums, and most of the time what we see here, like this particular line spectrum, is what's sometimes referred to as an emission spectrum. And that's because as those electrons are dropping down in energy, they're giving off the energy. So the atom is giving off the energy, it's emitting the energy. And that's what's referred to as emission spectrum. And typically when you do an experiment like this, where you kind of look at it, that's typically what you're looking at is actually the emission spectrum. It's actually when the electrons actually start dropping back down. And it's kind of like what we see with fireworks and stuff like that. It emits that energy in terms of waves, and we see all the different colors occur. So a lot of the times when we look at things is most of the time usually some type of emission spectrum, which is usually those electrons dropping back down. The opposite of that would be what is sometimes referred to as an absorption spectrum, which basically is when you kind of put the fire underneath like the element, it gains all that energy. And the transition is the electrons obviously going in this way, and it typically will correspond to obviously some different lines and colors. But when you would perform an experiment like this, you typically would know that it's more of an emission spectrum that you're looking at rather than an absorption spectrum. You would need some different equipment to kind of do the absorption part of it, what we typically would use for this type of emission spectrum. It's actually a very simple piece of equipment you can use for emission spectrum. It's like what's referred to as a spectroscope. You actually look through it. It has that prism in it, and you kind of line the spectroscope up with the light, for example, and then it will separate out all those colors for you.
Thank you.
You're welcome. Other questions? Okay. So one nice thing about sort of these emission spectrums is actually this, that every element will give off a very distinct emission spectrum, like what we see here at these lines. So literally, if you weren't sure what you were looking at, you could look at the main colors that you see and the actual wavelength at which those colors are at, and you'll be able to go, okay, that matches like hydrogen, or that matches like neon. So every individual element gives a unique sort of line spectrum that literally you can try to match up and determine what an unknown is. So what we're allowed to talk about here is those electrons, and electrons are found within an atom on different energy levels. And what we call basically the energy levels in an atom is this really big fancy word here, which is known as the principal quantum number. And really the principal quantum number is nothing more than a very fancy word for the energy level. And they're the energy level at which you can find basically electrons within the atom. And it is referred to as N. And N could have values of 1 through 7, for example. And basically, when you have a value of N equals 1, that is what is referred to as the ground state. And that essentially is the lowest in energy. And what that means is that sort of energy level is actually the closest to the nucleus. So that is the closest to the nucleus, N equals 1. Anything above that, like N equals 2, N equals 3, N equals 2 through 7, these are what are referred to as excited states. They are further away from the nucleus. So as you go from 2 to 3 to 4 to 5, you're getting yourself sort of further away from the nucleus, and those electrons are farther away from the nucleus. And again, they're referred to basically as sort of excited states. So electrons really can only be in certain energy values, as I mentioned kind of earlier. I guess I jumped a little ahead here in terms of the slide, but that's really what we're talking about when we're talking about that quantized energy. And again, it's really that staircase example. And just like when people walk stairs, right? For example, personally, me, I could kind of only like do one step at a time, right? Electrons sometimes could only move one sort of energy level at a time. But then you got the guy that comes next to you on the stairs that goes, well, I'll do like 2 steps at a time, right? And they have enough energy to kind of walk 2 steps at a time. Maybe somebody has enough energy to do 3 steps at a time, right? And electrons kind of work the same way as you're transitioning from one energy level to the next. But again, they will for sure either gain enough energy to go from one energy level to the next, or if they're working their way back down, they will lose exactly amount of energy to take them from one energy level down to the next. And again, that's really what they mean when they talk about quantized energy. It's just that, like I said, you have enough energy to go on this energy level to the next. You'll never find an electron deciding, I'm just going to hang out in between. They definitely will only gain or lose energy and enough to make those transitions actually occur. And I think there was a question earlier, and again, this is really the difference between those 2 types of spectrums that we sometimes look at when electrons absorb energy. So for example, if you were doing like a flame test, or you were shooting off some fireworks or some explosives in it. And when the explosions are explosives, I'll spit that word out correctly, hopefully. When they explode, this electron is going to gain all that energy. And that's what's referred to as an absorption. It's going to go from a lower energy level to a higher energy level. When the electrons decide we want to come back down, again, they need to give off that energy in the form of a photon of light. And that's what's referred to as like an emission. And that's where we see those emission spectrums, like those lines that we looked at before. So in terms of electrons, as they are traveling from one energy level to the next, if they go from a lower energy level to a higher energy level, they basically absorbed energy. And that's what's sometimes referred to as being a endothermic process. Absorb energy. When electrons go from a higher energy level to a lower energy level, they have to release that energy. And that's what is referred to as being an exothermic process, where you release energy. And again, depending on really the wavelength of that energy that's being released as to what you might observe. You might see colors if it does fall in that visible part of the spectrum. And again, you may feel heat or energy if it fell in the infrared part of the spectrum, but you wouldn't see colors. So just so we're clear, not all transition of electrons results in you, for example, seeing colors. Only the parts where those waves, the waves that come off, fall within that visible part of this of the electromagnetic spectrum, where we see the red, orange, yellow, green, blue, violet. Again, if you had one that fell off into the ultraviolet region, you wouldn't really see color. You would hopefully have some sunblock on, so you don't get burnt or anything like that. But again, not all transitions will result in actual colors that you see. Just those ones that sort of correspond to that visible part of the spectrum. Any questions on that there?
Professor, on the fireworks, because you mentioned it a lot, is
Yeah.
that a natural reaction, the colors that come on the fireworks, or is that
It
man-made
depends on,
created?
it's really sort of in a sense, I think what you're asking is how do they get certain colors? And it's basically based on sort of the elements that are present. So it's kind of like the same idea. Like if you look at neon lights, for example, you know, we sort of call everything neon lights that, you know, kind of light up like that. But there are different colors, right, of sort of neon lights, if you will. And it's really because within those glass tubes, there's different elements, and certain elements, you know, when you sort of excite it, will give off a certain distinct color and stuff like that. So kind of the same idea. I'm not 100% sure, you know, professional fireworks guy myself, but, you know, it's really based on sort of the elements that are sort of present within there as to sort of the distinct colors that you see. Other questions? All right, so take a look at this one. In each of the following energy levels indicate the energy is absorbed or emitted or released or not changed. If an electron moves from the first energy level, which is n equals 1, to the third, so basically our electron is starting here, it's going upwards, it has to absorb that energy to gain enough energy, like our stair example, to get itself up there to the third energy level from the first energy level, obviously skipping the second energy level in between. So that would be absorbed. Electron falls from that third energy level back to the second energy level. Again, in order to come down in energy, you have to give off the energy in terms of a photon of light, and that would be that it's emitted. And an electron moves within the third energy level. So if you have an electron that's just kind of hanging out there on the same floor, there's really going to be sort of no change that's going to occur there. Again, it's not transitioning from any energy level to the next. So there really would be no change in the energy. Any questions on those there? Yeah. So as I mentioned before, we talked about the principal quantum number. And really where we're kind of going with this is we're going to talk about electron configuration and how electrons are basically distributed within the atom. And, you know, n equals 1, which is the ground state, the lowest in energy. And again, it sort of builds up. And you could kind of think of these sort of energy levels as like floors in a hotel, right? You know, you go to the first floor, there's some rooms and you'll find some electrons there. Go to the second floor, there's some rooms. You know, you go to the third floor, there's some rooms, and so forth. And that's a good way to sort of think about sort of the different energy levels. Depending on the energy level, there's, you know, only perhaps certain options on that floor where you would find an electron. Just like if you went sort of through a hotel and you got off on a particular floor, there's only certain so many hotel rooms at which you could stay, right, on that particular floor. Maybe you go all the way to the top and there's only like the penthouse, right? One actual room or that you could actually stay at on that particular floor. And the electrons kind of work the same way in terms of their energy level. So we have these different energy levels, and where electrons actually are in an atom is they're actually found in what are referred to as atomic orbitals. And as I mentioned earlier, when I was talking about the electrons really don't travel in these pretty circles, which sometimes people refer to as orbits. This sort of quantum mechanical model, which obviously we're not going into giant detail about, we move away from the idea of orbits and traveling these pretty circles to the idea that we talked about, that really electrons are moving around in a pretty random pattern, but they are thought to be housed in what are referred to as atomic orbitals. And there's a few different types of atomic orbitals that we see here. The first really important thing to know and to remember is that any individual orbital you have could hold a maximum of 2 electrons. So any individual orbital you can hold basically would hold a maximum of two electrons. There are s orbitals, and s orbitals look like this, kind of like a spear, thought like the nucleus is kind of here. And really what all these things are hypothetical, sort of what are referred to as probability maps. So because we really can't say for certain, which is what is referred to as Heisenberg's uncertainty principle, we can't say for certain that electrons are moving pretty little circles. And like, if I put my finger here, I could just wait for the electron to come back around. And because they really do move in this random motion, the idea of the Heisenberg uncertainty principle is this: really a particle like an electron, the more you know about where it is, the less you know about how it's traveling, and vice versa. The more you know about sort of the speed and velocity of how it's traveling, the less you know about sort of its position and location. And that's what basically the uncertainty principle is all about. So what they sort of came up with are these atomic orbitals, which there's really more of what is sort of referred to as a probability map. And what we could say is in a certain location within the atom, there's a very high probability of finding an electron there. Not really sure how it got there, how it's traveling, but there's a fairly good shot of finding an electron there. As we know from our conversation here, we would expect that because the nucleus is positively charged, there should be a fairly high probability of finding an electron near the nucleus because positive and negative guys are attracted to each other. And that's really what all these sort of guys represent. If you pulled apart an atom, would you see an s orbital, p orbital, d orbital? No, they're really just sort of probability sort of maps. But we do have s orbitals, and they do sort of look like a spear in theory. And again, really higher probability of finding electrons sort of near the nucleus. And as you sort of fan out, less of a probability of finding it. One important thing is there's only one type of s orbital. So no matter what energy level you're on, there's only one type of s orbital that you have. They all look the same. They just get larger as you go from one energy level to the next, which means if there's only one type of s orbital, you can max out by putting basically 2 electrons in that orbital. Now, p orbitals, there's actually 3 different types of p orbitals. There's what's referred to as the px, py, and pz orbital. They all look like this: teardrop, figure 8, whatever you like to call it. But basically what the x, y, and z means, like in math, there's like an x, y, and z sort of coordinate in 3-dimensional space. And you got one of these p orbitals on each of those, the x, y, and z sort of axis in 3 sort of locations in 3-dimensional space. Now, since each of these individual orbitals could hold 2 electrons, when we take all of these guys together, these are sometimes referred to as a subshell or sublevel, depending on your book. And since there's 3 individual p orbitals, each one could hold 2. 2 times 3 is 6 electrons maximum if you filled up all of the p orbitals with electrons. Now, d orbitals, as you can see, has a slightly different shape. Kind of looks like 2 p orbitals put together. And there's actually 5 different types of p orbitals. Same idea as the p orbitals. There are 5 different types of d orbitals, and it's basically just their sort of location in 3-dimensional space. And because there's 5 different types of them, each one could hold 2. So if we filled up the d subshell, we could put a maximum of 10 electrons in there. And lastly here, f orbitals kind of look like 2 d orbitals put together. There are 7 different types of f orbitals. And since there are 7 different individual f orbitals that make up a subshell of f, 7 times 2 is 14 electrons. So within the atom, you could kind of think of the orbitals as like, again, the rooms on the floor. So for example, when we go to the first floor, the only orbital that's present is a 1s orbital. The 1 here means I'm on the first energy level. The s is the type of orbital I'm talking about. So this is like you went to the first floor of the hotel. Your only option is actually, instead of the penthouse being on top, the penthouse is on the bottom here. There's only one place that you can stay, and there's only one place for the electron to stay. When you go to, say, this second energy level, there's also a 2s orbital present. The 2 here just means that you're on the second energy level. The s means you're talking about an s orbital. And that's where we first start to see the 2p subshell occur. So what does that mean? When you go to the second energy level, you have a choice of 1 room, 2 rooms, 3 rooms, 4 rooms for which the electrons could actually be placed in. So you could kind of think of it as sort of like, floors in a hotel and rooms of where we sort of pocket the electrons as they really go into the atom, and that's really what we're talking about here, is the sort of filling order. And electrons do go into the atom basically one electron at a time, lowest energy first, and then continue to go to the next lowest, the next lowest, the next lowest, until all the electrons are basically kind of put in there. And again, as I said before, you know, sort of these are really probability mass. So again, this sort of area of an s orbital is really a pretty high probability of finding an electron. Not really sure where it's at. The nucleus is thought of being here. So kind of in this area of a p orbital on both sides, it's a pretty high probability of sort of finding an electron in those particular areas. Here's what I was talking about, a much nicelier drawn than what I did. The px, the py, and the pz orbital. Again, here, they're just really the same shape, but kind of different locations in three-dimensional space. And all three of those together are what are referred to as a p subshell or p sublevel. And again, basically put 2 electrons in this guy, 2 electrons in this guy, and 2 electrons basically in that guy as well. Any questions on that there? So the orbitals are really the places where we could put the electrons. And again, this is sort of like an energy level. So for example, here, this is for hydrogen. This would be like n is equal to 1. This is over here, n is equal to 2 energy level, n is equal to 3, and it's equal to 4. Again, as we put electrons in, we'll use arrows to represent them. 2 electrons here fills it, then we would go here, then we would move over to here, and again, sort of put all of our electrons in there at once. Again, not at once, but basically lowest energy to highest. Now, this is what hydrogen looks like, and there's actually a change that occurs when we put more than 1 electron in. And with 1 electron in hydrogen, you can see that everybody on the second energy level is perfectly equal with each other. Everybody on the third energy level is perfectly equal with each other. But it actually does change when we start to put more electrons in there than 1. Before we do that, I just touched upon it a second ago, some terminology that sometimes confuses people. So let's just talk about that while we're looking at this picture here. First off, sometimes you will be asked, for example, what is the maximum number of electrons you can put in a n equals 2? And again, the terminology here is either shell or level. So what are we talking about when we talk about a shell or level? We are talking about the n equals 2, which means we're talking about every single orbital that is on the second energy level. And that means that I could put 2 electrons here. I could put 2 more here, 2 more here, and 2 more here. And that's a grand total of 2, 4, 6, and 8 electrons. So if I filled up the entire n equals 2 shell or level, you could put a maximum of 8 electrons. Now, if I were asked, you know, what is the maximum number of electrons if you fill the 3p subshell or sublevel is sometimes called, what am I talking about? I'm talking about the subshell or sublevel. That is not the entire n equals 3 level. It is simply these 3 p orbitals together. If each of those lines represents a p orbital, that would be a subshell. This would be like px, py, and pz. That is a subshell or sublevel. And again, I could put 1, 2, 3, 4, 5, and 6 electrons in there. And the answer would be 6 electrons. Question on that. Just like this right here, what I'm circling would be the 3D subshell. And again, you could put basically 2 electrons, 2 electrons, 2 electrons, 2 electrons, 2 electrons, which would fill up with the 2, 4, 6, 8, 10 electrons in that particular case. Now, if I asked, you know, how many electrons could you put in a, we'll do a 4D orbital. Now, how many electrons can I put in a 4D orbital? This is usually the trick question. If you remember a second ago, I said any individual orbital can only hold 2 electrons. So we're not talking about all of these guys together, right? Because all of these guys together would be the 4D subshell. We're talking about an individual 4D orbital, which could be that guy, could be that guy, could be that guy, could be that guy, or could be that guy. And no matter which individual one we're talking about, it could only hold a maximum of 2 electrons. So you want to be careful on sort of the terminology here. Basically, if somebody says shell or level, they're talking about every single orbital that's on one of those N values. If they're talking about a subshell or sub-level, they're talking about, for example, like all the 3p orbitals together, all the d orbitals together. If they're talking about an individual orbital, they're talking about just one individual orbital that could only hold 2 electrons. Any questions on any of that there? So what happens as we put more than one electron in there, if you take a look at it before I scribbled all over it, there's actually a shift in terms of the energy of these orbitals, and that affects really how the electrons go in. So for example, because of there's this shifting that occurs, what we would see here is electrons would go here first. They would go here first. They would fill up all these guys first. They then would go here as the next lowest. They would go here. And the major difference that occurs is actually right here. People go 3s, 3p, 3d should come next. But actually what happens is the 4s is lower in energy than the d. So the 4s guy would actually get the electrons first, and then it would go back to the d. And that pattern repeats. We see again here, 4p, 5s, back to 4d. So there's really an order at which these electrons go into the atom. And this is basically where you can create it yourself, this one or this one. And either one of these is the actual order at which you can fill an atom. And the importance of this, or the way that this is very easy to do, is on the first energy level, there really is, I'm actually going to go back here and take a look at it if I can. Do it this guy. So as we can see here, again, if you ignore my scribble, on the first energy level, we have s orbitals, and s orbitals on every energy level after that. It's not until we get to the second energy level that the p orbitals start to appear. And then we have p orbitals after that. It's not until we get to the third energy level that d orbitals first appear. And it's not until we get to the fourth energy level that actually the f orbitals appear. So first energy level, only s's. Second energy level, that's when the p orbitals start. Third energy level, that's where the d orbitals start. And the fourth energy level, that is where the f orbitals start. Knowing that, it makes recreating this really easy, because all you have to do is go 1s is where the first energy level, that's what the 1 stands for, and that's where the s's start. It's not until I get to the second energy level that we have p's to start. It's not until I get to the third energy level that we have d's to start. And it's not until I get to the fourth energy level that we have f's. And literally all you have to do is fill in the numbers underneath it. 2s, 3s, 4s, 5s, 6s, 7s. Starting under the 2p, 3p, 4p, 5p, 6p, 7p. Starting under the d, 3d, 4d, 5d, 6d, 4f, 5f. So this is something that you could recreate really well and really easily. And how we use this is we always start here up on top. And basically we kind of zigzag back through it. So we go this way. Then when we're done there, we come back this way. We come back through this way. We come back through this way. And there's our 3P to the 4S, followed to our 3D and so forth. And obviously continue the drawings all the way through there. But we always start at the top and we zigzag back and forth. If you know how to recreate this or know this, and you know basically what we talked about a second ago, that you can max out an S orbital with 2 electrons. You can max out the P subshell with 6 electrons, max out the D subshell with 10 electrons, and you can max out the F subshell with 14 electrons. You pretty much could write any type of electron configuration that you would need to do. So let us do that. Let us write and talk about how to write proper electron configuration. And electron configuration basically tells us how the electrons are filled into the atom. Now, we always, in most chemistry classes that you do, write electron configuration was sometimes referred to as filling order, how the electrons actually go into the atom. You Google around and search around, you'll sometimes see electron configuration written in terms of energy. And I'm going to say that's incorrect for us, not technically incorrect, but it's incorrect for us in here. And most chemistry classes that you do, you should always write it how we're going to talk about it here, again, in terms of filling. So how do we know how many electrons somebody has? Well, if we're talking about something that is neutral, as we talked about earlier, the number of electrons, which are negatively charged, would have to equal the number of protons. And that means if we know the atomic number, we actually know how many electrons there are, because it has to have an equal number of electrons to protons. So let us take a look at sort of how things go in and how we write the electron configuration here. Let me just kind of move some things around here. All right. Let's start with the first one. And again, what I'll do maybe is recreate that real quick. 1S, 2S, 3S, 4S, 5S, 6S, 7S, 2P, 3P, 4P, 5P, 6P, 6S, 7S. I'll learn to count as late. 3D, 4D, 5D, 6D, and 4F, and 5F. Okay, so we're always going to start here and work our way. All right, so let us start with hydrogen. And hydrogen has the atomic number of 1, which means it basically has 1 electron. So we start at the top and we would write 1s1. So what do these numbers represent? The first one is representing the energy level. So we're saying we're on the first energy level. The S is telling us that we are talking about the electron being in an S orbital. And the number on top is how many electrons there are in the particular orbital, our subshell, and that happens to be 1. So 1s1, the second one here on the top, does need to be a superscript. I'm going to show you sort of what is sometimes referred to as an orbital diagram, just to show you how the electrons sort of go into the orbital. So we're going to pretend that is our 1s orbital. The first electron would actually go in, represented by that arrow pointing upwards. Is sometimes referred to as having positive spin. Electrons have their own spin, not really important for us, but the first electron, if you sort of draw what is referred to as an orbital diagram, always should be pointing in the upward direction. Any questions on that so far? Let's then go to number 2 on the periodic table, which is helium. Helium has 2 protons, which means it has 2 electrons. Again, we come back here and we start here, which means the electron configuration for helium would be 1s2. Again, the first one tells us we're on the first energy level. S tells us we're talking about the electrons in an s orbital, and we now know that we have filled that s orbital with 2 electrons. So if we draw sort of the orbital diagram for that, the first electron goes in, and there's something referred to as the Pauli exclusion rule, which is not important for us, but it basically tells you that the first electron that goes into an orbital will go in this upward direction. The next electron will go in the opposite direction, kind of pointing down. This is what is sometimes referred to as being paired spin. They sort of cancel each other out. Now, if each of those arrows represents an electron, I'm sorry, this should be a 1s. Sorry. Get rid of that there. Wrote the wrong thing. Again, this should be, obviously, we're still in the 1s. We have now put 2 electrons in this individual orbital, which means it's actually full. It cannot take any more electrons. So what happens when we have more electrons? So let's go to lithium, which is number 3 on the periodic table. Again, starting way back here at the top, it would be 1s2, which obviously is what we had here. Now I need to come down and zigzag back, taking me now to 2s, and I only need to put 1 electron. You could count up the actual top number to tell you how many electrons you put in there. 2 and 1 is 3. I have now distributed all 3 of my electrons. And if we were to sort of draw what that looks like, we would have a box for our 1s electrons, which first one would go in, second one would go in. Now we would go to our second level orbital and put 1 electron in, going in the upwards direction. What does all this mean? Well, this means that if we look at the electron configuration, we have on the first energy level 2 electrons. On the second energy level, which is what that 2 represents there, we have 1 electron there. So we have 2 electrons that are closer to the nucleus on the first energy level. We have 1 electron that is higher in energy on the second energy level. Excuse me. Any questions on that there? Let's continue on to beryllium, which is 4 electrons. Again, starting back at the top, it would be 1s2. We're now filled. We would zigzag back to 2s2. That would now fill it up. And again, if we were to draw our sort of pictures here, these orbital diagrams, up and down, that is filled. Up and down, that is filled. That means if we have more electrons, we need to zigzag back. And the next place we would go to is actually the p orbitals. So let's see what happens there when we get to boron, which is number 5 on the periodic table. Again, starting at the top, we would go 1s2. We would then zigzag back to 2s2. Now it is filled, as we could see earlier. We would zigzag back, and now we're going to 2p1. Now, if we were sort of to draw these guys, we would have a 1s, a 2s. And if we remember, the p has 3 different types of orbitals. We would actually have 3 lines to represent each of the 3 orbitals. That would be like our px, py, and pz orbital. And it would feel like this: 1 up, 1 down, 1 up, 1 down. First one would actually go over here in the upwards direction. What does that mean in terms of where our electrons are in terms of energy levels? On the first energy level for boron, we have 2 electrons. On the second energy level for boron, we actually have 2 here and 1 more here. They are both 2, which means that is 3 electrons on the second energy level there in boron. Any questions on that there? All right, let's continue on with number 6, which is our good friend carbon. Again, starting at the top, it would be 1s2, 2s2, 2p2 at this point. Again, we would have up, down, 2s, up and down. And just to show you sort of how the electrons go into a subshell like this, the px, py, and pz. First electron goes here, and there actually is a rule that says the next electron actually will go into the next orbital in the upwards direction. And how they actually go into these orbitals, they go into each orbital one at a time, and then they come back and pair off. So when you have a subshell that has multiple individual orbitals, the electron always goes in up to the first one, up to the second one, up to the third one. And if that's the p orbitals, then goes back down, down, and down. And that's just sort of a rule, really not too important for us, but that's really how they fill it. I just want to kind of show you what happens. And again, they would go kind of one at a time and pair up. Number 7, which is nitrogen, would have an electron configuration again starting at top, 1s2, 2s2, 2p3. And again, the third one would come here. And I'm just going to borrow this and steal it there. So I don't redraw it. The third electron at that point would go in there. And at this point, the next electron would come back and start filling. And that happens at number 8, which is oxygen here. Again, 1s2, 2s2, 2p4. Again, at this point, the fourth electron would go back to the first one and start pairing it up. And we might as well finish the first 10 here. Fluorine, which is 9, 1s2, 2s2, 2p5. Again, that fifth electron would go here. You could hopefully see from this picture that the p subshell only has room for one more electron, and that happens at neon. I can get my thing here right. There it is. Neon, which is number 10, 1s2, 2s2, 2p6. And again, that would obviously, as you can see, fill out the subshell there. Question on writing electron configuration here.
Professor, does that same rule apply to like the 5D and 5S where you have to fill them up first going up and then down, or is it only for the
So if your question is if you got to like a D subshell, you know, where you have say, like 3D, absolutely, they do fill that way. They would go one at a time, and then they would come back and basically pair off with everybody.
All right. Okay. Thank you.
Yep. And really for us, you probably don't have to worry too much about the orbital diagram. You know, I just want to kind of show you kind of how the electrons go in. You do have to be able to obviously write the electron configuration correctly, like we see here. So for example, let's take a look at, let's do, why don't you do calcium and see what you come up with. So calcium is number 20. So take a minute and write the electron configuration for calcium. So again, we would start at the top. So we would go 1s, right, let's try it again. 1s2. That takes care of that. We then would zigzag back to 2s2. Again, if we count up the top numbers, that's 4 electrons. So we would zigzag back to 2p, and that's a p subshell, which means we could fit 6 in there. Again, if we count the top numbers as 2, 4, and 10, we then would go to 3s next. We could put 2 in there. So that is 10, 12. We would zigzag back to 3p, which is a subshell. And we could put 6, and I need to count now. That's 2, 4, 10, 12, 18, close. We then need to go, again, it is the 4s that comes next. And it would be 4s2. So again, it should look like this. It shouldn't be big numbers. There's no commas. There's no dashes. This is proper electron configuration. Any questions on that? Now, just to end with this, if we look at this configuration up to this point, how many electrons is up to that point? If we count up the top number, 2, 4, 10, 12, 18. If we look at the periodic table, 18 is argon's configuration. So we can do a shorthand where we put argon in brackets, and that implies argon's configuration. And then we would continue with the rest of it and do this. So argon 4s2. This is what is sometimes referred to as noble gas configuration, which means when you go to do this, it always has to be a noble gas that's in the brackets. And it's the noble gas that comes right before whatever you're writing the electron configuration for. And then you just continue on with the rest of the configuration. Any questions on that there? Again, that's sometimes sort of a shorthand way of writing electron configuration. All right, then we will lay it up there. We're almost done with this chapter. So